Good morning. Good evening, everyone. Let us start today's session. I hope I'm audible. Good morning, everyone. Yeah, let us start today's live session. Welcome all of you for the week 8 live session for the Smart Grid Basic to Advanced Technologies NPTEL course, and I am one of the TAs for this course. My name is Gagan Meena, and I'm a PhD, fourth year PhD research scholar at IIT Bombay in the power electronics and power system specialization of electrical engineering department. Let us begin today's session. We will be following the same agenda which we have been following till now. We will discuss an overview of week 8 and then we will discuss certain questions and you can ask your doubts whenever you want. And these are the deadlines for the assignment 8 and 9. You have to submit the assignment 8 by March 19th and assignment 9 by March 26th. And I hope all of you are able to access the recordings of the live sessions. And this is the link for the recordings of all the live sessions. It's the YouTube link, and you can easily find it out on in the problem solving sessions tab. There you will find link for each live session by each of the TAs, and also you will find the link for the Google Drive where the material used for these live sessions is also available. In this week 8, we discussed wide variety of topics. For example, like this PMU placement, which is related to our previous week where we have discussed the discrete Fourier transform. So we have discussed that how using PMU can help us do the wide area monitoring of the entire system. And we also discussed how does the PMU estimate the voltage and current phasors using the discrete Fourier transform of the signal, which is the input voltage and current signal. And we also discussed different types of techniques for doing this phasor estimation. For example, we discussed different techniques for phasor estimation, which is essential output of or the work uh, of the PMU. One we did full cycle DFT. We also discussed half cycle DFT. Then we discussed cosine transform and sine transform also. And then we also discussed least square. Least square error based state estimator and state estimator, phasor estimation. And we didn't discuss this, but it was also one of the techniques, unique filter. So we discussed all these things, and now here we are discussing So this is the work of the PMU. PMU will do the phasor estimation. Now, but we have to see, we would like to have the voltage and current phasor for each and every bus, right? But if you want to place PMU at each and every bus, then it's very costly affair. The question is, can we do something where we need not place PMUs at all the location and yet we are able to achieve the desired goal which you want to, which is to observe, to have an estimate of the state of the system at each and every bus. For that, we use this optimal PMU placement. So what it tells the output of this will be the minimum number of PMUs and their location required to observe the entire system. Then next topic we discussed was cybersecurity and resilience. We all know that with the increasing these advancements in IoT devices, communication infrastructure, technology like cyber physical systems have evolved and everything is becoming more and more the interaction between the physical and cyber layer is increasing at a rapid rate and which always has this potential of cyber theft, cyber attacks. And for that, we need to protect the system. We need to ensure that the system is secure against any kind of cyber attack and also it's resilient. That whenever something, not only it mitigates any kind of cyber attack, but it also brings the system back to its normal operating conditions once there is an attack. So how quickly the system is able to recover from that attack once detected, that is very important. The next term concept which we discussed was of virtual inertia and ancillary support. We know that with the increasing RE penetration, the inertia in the system reduces because the inertia is the inherent in the conventional generator because of this large rotating mass, which is the straight error rotor, the rotor of the generator. That because it's a huge mass, it has an inertia which naturally damps out the variations in frequency, right? But this is only possible for the conventional resources because the distributed generators, especially PV, are energy storage. They are inverter-based devices, and in their natural position or their natural configuration, they cannot provide any kind of inertia because they are static devices. They have no rotating mass, rotating part. That's why a concept of virtual inertia has evolved where we want try to mimic the behavior of these conventional generators by doing some maneuvers in the inverter operation of these DGs, distributed generators, and thus they are able to provide different kinds of ancillary support services as well. Then finally, we discuss that as the utility grows, as the time passes, the load of the utility generally increases. It might not always be the case, but yes, it does increase, especially for a developing countries like India. It will increase, and if the peak demand increases, then we need to build up, the increase the generation, and because we want to reduce the greenhouse gases and global warming, we don't want to add thermal generators, but therefore we are adding these renewables, the solar and wind. However, we also know that the peak demand and the peak solar or wind generation do not match. The peak PV generation is during the daytime and the peak is during morning and evening. Similarly, the peak generation from wind is during late evenings, while the peak demand occurs in the early evening between 6 to 8 p.m. And thus there is a mismatch. So using simply the renewable generators will not always be will not always be sufficient because of intermittency, its intermittent nature. There might be cloud cover or some extreme weather situations where the output from the wind or solar reduces drastically. In that case, to meet the peak demand, thermal would be required. It would be essential for that purpose. However, we also want to reduce these emissions from the thermal generator. That's why if we can do something to minimize the load itself, then our problem will be solved. And that comes in demand side management, where we will devise certain policies, we would have certain incentive-based, price-based mechanism which can attract the users to reduce or even alter their demand pattern or load pattern as per the requirement from the utility or requirement of the utility. And demand response is a subset of demand side management. We would see that. Yes, so now we are moving. This was the overview of what are these different topics which we discussed in this week. Now we will go through them one by one. The first one is our PMU placement, optimal PMU placement. Okay, so PMU placement, why do we want a PMU? Why are we talking about PMU placement, the two optimal? Because here it is mentioned, you can see the increase in uncertainty in generation and demand, and it increases the necessity for real-time monitoring of system state testing of for real-time monitoring for state estimation. However, the installation of these PMUs is limited by economic and infrastructure constraints. That's why we want to monitor at least the critical. I'm sorry. Thus, we want to uh, have information about at least the critical buses, generator buses, tie line buses for close monitoring. And because PMUs are costly, their optimal bus location is calculated is of prime importance. So here we see this is a linearized DC power flow. It's an optimization problem where the objective is to, sorry, this is linearized DC power flow. Here the objective is to minimize the operational cost of generator. You can see this is the minimize here. Innovation of PIG, I is equals to 1 to NG. The operation cost of generator 1 of I generator I into the production of generation I. Here now we have the network constraints, which are the power balance, line flow limit, and power generation constraints. So power generation constraint that the generation has to be between the minimum and maximum limit. And the line flow limit also has to be between minimum and maximum limit to delta I minus delta J. If this is node I and this is node J, and we have assumed current flows in this direction, then delta I minus delta J upon Xij is the sorry is the line flow between bus I and J, and that has to be between the maximum minimum maximum limit. Minimum is the maximum in the opposite direction. So if this is a line between bus I and bus J, then and if the current flows in this direction, this is the reference direction, then the maximum power flow is Pij max. And if the actual power flow is in opposite direction, in the reference direction, then the limit will be minus Pij max. That's why it's written like that. Okay. So because in that case that this will change. We want delta I minus delta j upon xij to be less than some limit, right? Yeah, but if the current flows in opposite direction, then this will become delta j minus delta I upon xij less than equals to P max. And this one is the power balance constraint at each node. Generation minus demand is equals to the total injection is equals to sum of line flows originating on the lines originating from that bus I. So this was for linearized AC power flow. Hey Krishna, sorry. And this is for the PMU placement. Here, the objective is to minimize the overall cost of placement. Here, CPMU is the cost and XI is a binary variable. So if a particular PMU at a particular bus is selected, then it will add to the cost, otherwise it won't add. It would be simply zero. Now we have two types of constraint here. One is the constraint observability constraint and second is the state estimation constraint. Observability constraint is that from bus I, summation of xi, where I belongs to n bus should be greater than equals to 1. For n, every n bus belonging to I as a bus. Summation of xi is greater than equals to 1. Now let's move on to the cyber physical system. The cyber physical system is a very important concept which has come up and it brings out the multidisciplinary nature of the power system, especially. In the first diagram here, we can see that there are two layers. One is cyber layer, one is physical layer. I could say there is one cyber system and one is physical system. And this cyber system interfaces with the physical system very easily. So there are two layers, one is cyber layer, one is physical layer, and there is another layer which is we can call communication layer, which is in between the two, which is responsible for the two-way communication or the two-way flow of information between the two layers, cyber and physical layers. Here you can see from physical system is all, it's an analog system, and our cyber system it works in the digital level. So we need to convert the digital signal into analog system before giving it to the physical system. Similarly, from physical to this, the from physical to this cyber system. cyber layer also. The physical is analog and cyber works in digital. So we need a ADC, analog to digital interface or converter. Here we can see in same thing is shown here in the second figure also, that there is a cyber system and there is a physical system where physical processes are happening through actuators and sensors, and then there is a communication network between the physical layer and this cyber layer. From cyber layer, the actuators, they receive the actuators in the physical system, they receive information from the cyber layer, and then the actuator performs some function, and then again it can it can send some data, and the physical process can send some data and give it to the communication network, and communication network will give it to the actuator to again do certain changes if required in the physical process. The cyber means there are three things. One is the communication, which is the protocol, different types of communication protocols. Second is compilation of, not compilation. Second is the computation aspect. So first one is communication, second is computation, and third one is the cyber or the control system. So we can say there are total two layers. One is cyber layer, one is physical layer. And in cyber layer, there are three components. One is the communication, including the different protocols for communication. Third one is the computation aspect, where the analysis happens. And last one is the control system, or the IED, intelligent electronic devices, or IoT devices. So this is an example of the cyber physical system here. Above you can see the information control system, and then there are different types of data which are to be communicated to the physical system. For example, the meteorological data, real-time data, historical data, information platform and fault identification, dedicated wire network, automated sense system, wireless network system with regional data collective system. All these systems, they will collect data from the actuators in the field device, and then whatever decision is taken, that is to be communicated to the sensor via the device again, and it goes there, and then different types of analysis can be performed. These are the, you can say, components, different components you can see here. Here you can see the difference between the two systems. One is the physical system and cyber system. Here components in physical system are all the physical components like generators. So in power system we have three main component. One is the distribution, transmission, and generation. And in physical system we have all these three. So we have generator, we have transformer. So all the physical components, physical assets which are there on these three levels, generation, transmission, distribution, will come into the physical system. For example, generator, transformer, line, the transmission line, the circuit breaker, relay load, etc. While in the cyber system, we already discussed, there are three components. One is the computation aspect, one is communication system, and another is the control system. The nature of system is physical is continuous, and here cyber is a discrete. That's why we need ADC and DSC blocks for communication from physical to cyber, and vice versa. Modeling here of physical system is a differential algebraic based, and cyber system it's difference based. And here you can see system model is energy flow, and here cyber physical it is information flow. Branch model in physical system is power grid model, and in cyber system data transmission, data processing, and data pool is being used. And what's the condition for the physical system? It's a nodal balance and line limits. While for cyber system, it is independent of operation, balance among controller, computing, and communication functions. There can be contingencies like line fault, internet outage, load outage, etc. While here in cyber system, the cyber attack, communication latency, malicious control effects, etc. are seen very commonly. Stability and security, the power system stability and security is good now. Saying that network control system stability and cyber security. So in physical system, we are talking about the stability and security of power system. And here we are talking about the stability and cyber security of the networked control system. Okay. Next, moving on to advantages and disadvantages of cyber physical system. Here we can easily see what's the advantage. Advantage of cyber physical system include two-way communication, the two-way flow of information and electricity. Then there is efficient, safe, and secure operation of power grid. Then we can have flexible, coordinated operation based on global system variables, automation, and smart features for the power grid. Disadvantage include the cyber attacks, communication latency, package dropouts, network jamming or congestion, malicious control effects. And these are the different cyber adversaries examples you can see starting from 2010 in Iran, Stuxnet, destroying uranium enrichment infrastructure, and 2011 US control center software exploitation, 12 Germany internet communication system offline, 15 Ukraine black energy attack widespread blackout, 2017 again Ukraine WannaCry attempted encrypt data and demanded payments. 2019 US power generation system and control centers failure. 2020 Germany power generation system and control center failures. 21 Australia ransomware attack on energy generators. 21 India Red Echo 10 power assets. Mumbai, Tamil Nadu ports. And these are the different types of cyber attacks. One is the FDI, false data injection attack, and DOS is a denial of service. The false data injection algorithm, there are these avenues where false data can be injected, for example, sensors, controllers, and in the communication link as well. So in this case, what happens is that let's say the actual generation for a generator, it's the actual generation. PG actual was 50 megawatt, but cyber attack is showing it as 55 megawatt. And there is a difference of 5 megawatt in generational load, and it will increase. That will decrease the frequency. Similarly, the controller was supposed to act at MPPT during the daytime peak hours. However, the malicious attack says that no need for PV to be on. And if it's not on, how the storage will be charged? So it's a problem. Okay, similarly, denial of service attack, there is a man in the middle or suspend communication. Either suspend the communication as it is, or there is a man in the middle, and it can be both unidirectional and bidirectional. That means the actual data is going to another person, and which is not giving service, which is stopping that next step of sending data to the control center, actually wherever there is a requirement, or even get processing from there. So it can be unidirectional as well as bidirectional, man in the middle. Now let us move to the next one. So these here you can see an example of cyber attack. Here you can see the power distribution is there. You have distribution SCADA, you have feeder buses, you have field devices from where field measurements are coming, feeder buses where pseudo measurements are coming here, and it's going to the distribution SCADA. If there is an attack, we can say attack vector A. So it can happen to the feeder devices or feeder buses. It can happen to field measurement or pseudo measurement. In distribution control system, the state estimation is important for the demand side management, capacitor switching, and feeder reconfiguration. So these are the different types of the false data injection threats in active distribution system. The first one is end user level. Here we have energy management or advanced metering infrastructure. So in this AMI, there can be communication network and smart meters. In energy management, we have energy storage, smart energy management, and PV system. In field devices, a voltage regulator, micro PMU, IED, control center volt power control, distribution system, state estimation, which can be balanced single phase distribution or unbalanced multi-phase. Then energy pricing and trading, distribution, locational, marginal pricing, real-time pricing, transactive energy market, peer-to-peer distributed energy trading, all these things are possible. And all these things can be affected by the false data injection. So we need to protect all these areas. These are the areas which are prone to the false data injection. So all these things can be um, corrupted by the cyber attackers. So here we can see another different impacts of cyber attack. One is we can say the first one is the impact. It will have economical impact as well as a physical impact. Cyber attack can impact on frequency control, protection system, root triangle stability, all these things. And then construction is attack on state estimation, attack on voltage regulation, and attack on frequency control, attack on protection system. Defensive strategies, we have strategies based on protection, strategies based on detection or mitigation. Cyber attack, number of protected sensors and their locations are determined based on the budget, the sensitivity of the system, etc. And the meters and sensors are protected against cyber attack. Cyber attack can be classified into dynamic detectors and static detectors. The measured data are analyzed to detect attack and mitigate its adverse effect on the smart grid. Then we have two terms. One is pertaining to the cyber physical system. One is the security aspect. Another is the resiliency aspect. Okay, so security means to protect against and avoid the increasing threat from cybercrime. And resilience, we have physical resilience as well as cyber resilience. The cyber resilience means to mitigate the damage, system processes and reputation, and to carry on one system or data have been compromised by isolating the compromised part and continue working with the healthy part. And third one is the resiliency of the communication systems. We have three, or we can even include the communication in the resilience part because you would say the cyber layer is having three components. One is communication, one is electronic devices, and that we have already seen. Communication protocols, computations, and the control system or IT devices. So these are the different approaches for cyber anomaly detection. The first one is the centralized here, knowledge based, and it's knowledge based and data driven. You need to keep track of the daily prices, what's the time of. There's so much data is required here to understand when was there, when the cyber attack has been there, what was the condition there, what was the situation when the cyber attack happened, and how did the system behave in that case, and what was the response, how was it mitigated. All these things are studied to avoid any kind of mistake in the future. And it's knowledge based and data driven, and there are different methods like state estimation, chi square, residual based binary hypothesis, and model free ML statistics. Decentralized approaches, they are robust not only against disturbances and measurement noises, but also against incomplete measurement. This is very important. Here we need complete information about each and every device. And once the link between that particular device is lost, we'll not be able to know the state of that particular node. However, in decentralized, it is much more robust. Here, these centralized is robust only against disturbances and measurement noises. However, decentralized is also immune or robust against incomplete measurement. Centralized methods after approximation. This is an example of decentralized. Another example is singular value decomposition. And then last one is fault detection and identification. It can be observable based also. Now moving on to the third part, which is the virtual inertia part for us. The control of inverter-based DGs in such a way that it mimics the conventional synchronous generator dynamics and provide the inertia virtually. What are the sources of inertia? The short term in case of virtual inertia, the source of inertia is the short term energy stored in the DC link of the renewable energy source power converter, enabling converters and IBDGs to mimic the behavior of conventional generators. Then virtual smart grid. It provides grid support services, inertia, frequency regulation, voltage support, and it can be tuned by a software adjustment. That is a very big advantage in this case for virtual synchronous generator. Now we will see the the frequency response services required here. Here you can see the all India demand met. It's the all India demand met for 17 Feb 23, and the peak is around 210 gigawatts. And this is of 17 Feb. Regional demand met plot. So demand for each of the regions, and this is all India generation plot for the same day. Here we have PV, and the net load is reducing here. The green one is the red one is the total. And in inertia, there are four, it works on four levels. First one is the inertial, this virtual inertia or inertia analysis. The first one is our inertial response, which is inherent in each of the generators because it's a rotating mass. Inertia is there. That is the first one. And its time of cycle is its time is few cycles. And that is the first one. Then next is primary, then secondary, and then tertiary. These are the three. The total four are there, and they were one after another. The initial response is not able to bring the frequency back to its nominal value. Then the primary response kicks in, and after some time, the secondary will also comes up when there is an imbalance in the exchange between the two areas, two or more areas. Then the secondary also comes in, and then finally the tertiary one. It's a very long duration ancillary service, tertiary one. And here you can also see the time which we spend for different types of services, or the time, not time spent, it is the time required, or the timing for different kinds of seva. We would rather say that. So here you can see unit count on day ahead scheduling can be done much later on the day. So this is what we were talking about, the all India demand curve. Here you can see four characteristic divisions of this plot, the peak demand plot. Here you can see two peaks. You can find one in morning, one in evening, and you can find two lean. One is at night and one is during the daytime. So the objective of this uh, demand side management is maximize the economic benefit, maximize the power imported from the main grid, not maximize, minimize. We want to minimize the power imported from the main grid so that the losses are reduced and we can get a smaller bill also, and reducing the peak load demand. Here you can say the Indian demand, you are seeing it, it is having so much difference between the peak and the minimum, you can say minimum value here. And for this we need to have thermal generators because we don't want to buy RE which are more polluting to the environment. If we get thermal generators to reduce this peak demand, then although we can reduce, but it will increase the environmental pollution, and we want to avoid that. So can we do something to reduce the peak demand while also uh, not while means avoiding or deferring the up generation or of new deities? Is it possible? Can we avoid deferral for this installation of new generators or new thermal generators? So that can be achieved using the demand side management, where we are able to alter the load curve. So these are the different objectives of demand side management. We want to minimize the use of minimize the power imported from main grid and maximize the use of renewables, maximize the economic benefit and reducing the peak load demand. This demand side management can be single objective or multi-objective. Single objective, because here we have two entities. One is the utility and another one is the consumer. So both of them would want to increase their benefit. So single objective would mean that the operator would minimize only the benefit of one of the two. Okay, and multiple objective means both of their objective is we try to meet the both. Because here, let's say we have one actual, or you can say forecasted. We want to minimize the difference between the actual load shape and the desired load shape. And now this load shape can be for both the utility and the consumer. So we want to minimize the difference between this actual load and the desired load shift. So this load shift is either for utility or the consumer. However, in the multi-objective system, we want to minimize this actual load shift minus 0.5 of this desired utility load shift minus 0.5 desired utility नहीं consumer load shift. These are the 6 methods of 6 strategies for demand side management. One is the peak clipping. So what is done here is we try to reduce this peak demand. Is it possible to do that? Yes, it's possible. How can we do that? We can do that by using energy efficiency devices. Energy efficient. Then next one is valley filling. Here the axis scope, this axis peak demand is shifted both the sides. We are trying to fill the valley. Our main aim is to achieve a flat load profile like this, but we cannot have it. It's very difficult, and because of the economics, so much extra additional generation is required just to meet the peak demand here. Right. That's why this excess generation, excess load during daytime, it will be shifted to the night time for the early morning. And this will help in shifting in valley filling. And third one is the load shifting. Sorry. In this valley filling, we are trying to increase the output. This load in the off peak hour or peak hour. And in load shifting, we are shifting this excess load during this peak and these off peak hours. Strategic load growth means there is a new, I would say, new colony, which is for a similar type of load growth. We have given that a strategic load growth. Similarly, there can be strategic conservation as well. And then the last one, the most advanced version is the flexible load shift, which can change its shape as and when required. So here we come to different types of the demand side management. The first one, demand response is a subset of demand side management. The first one is using energy efficient devices. We can replace the less energy efficient equipment with the new high energy efficient devices. Then next is energy conservation. So this can be done by changing the consumer behavior where they can shift their actual usage of electricity during early morning or during late nights. That will save you money also, lot of money. And then last one is the demand response. It is three types. One is control strategy based, second is price based, and third one is the load based. The control strategy based can be both centralized as well as decentralized. However, using even a single link will render you in a difficult position. All in distributed, even if you miss single point, and it's not a problem in my approach. So that's a control based, strategy based. Now, next one was a price based. This can also be two types. One is a dynamic, using dynamic pricing. Here, there are three types of dynamic pricing. One is time of use tariff. The different tariff for off peak and peak hour. Different price for the two time, and critical peak pricing even in price when time when the price is high for the time of use tariff. There, during those time for few minutes, if the price is really high, that is the critical peak pricing. You can see here this was a normal time of use tariff where there are two tariff for peak time and off peak time, but here in critical peak time for a particular hour or two, then there is a more increase in sudden increase in the price due to the high demand there. It increases the price to a very high level. Then real-time pricing, it based upon the real load of the system. It requires each communication infrastructure is required for that. And then apart from dynamic pricing based, there is incentive and penalty based. And the three examples are in this case direct load control, interruptible service, and demand bidding. Last one is a load based. Here we have two types, task related and energy related. In energy related, energy is done, but there are still some solid left. So energy related means you cannot shift, cannot change the time of operation, but you can reduce your energy consumption. Task related, it doesn't matter what's the task, it has to be completed within the same day, or within the time frame which is there. Today we discuss everything so quickly, and now let us move to the questions. Again, you can discuss all these things in more detail if required, and the questions are very challenging. The first question is which of the following statement is are correct with regard to the optimal PMU placement and distribution system? The first option is PMU's installation is highly economical. Second is observability constraint is an essential part of optimal PMU placement formulation. Particle form optimization is one of the classical optimization techniques. The optimal minimum number of PMU for IEEE 1 minute per system is 30. So now we have to choose. So here A is PMU installation is highly economical. If this was the case, then we would not be talking about optimal PMU placement. We want to optimally place PMU only because they are very costly to install at each and every bus. That's why we are trying to place them optimally. So this statement is not correct. Second is observability constraint is an essential part. Yes, it's an essential part. We require that. We want the system to be observable with the minimum number of PMUs. Then particle swarm optimization is one of the classical techniques. No, it's not correct. Not at all correct. The classical optimization techniques involved this MILP, intelligent programming, NLP, or this graph-based approach. Particle swarm, genetic algorithm, all these are meta-heuristic techniques. not classical optimization techniques. And then optimal minimum number of PMUs for IEEE 118 bus system is not 30, it is 28. So we would say which one is correct? This is not correct. And this is also not correct. And this is also not correct. So only B option is correct here. Here you can see these are the optimization techniques. One is the classical technique. One is the classical optimization technique. Here we have binary program, binary linear programs, then mixed integer linear program, non-linear programs, graph theory based. These are the four classical optimization techniques, and last second category is the meta heuristic techniques. And here example include the genetic algorithm, particle sum optimization, tree search, and topology based. Okay. So here option B was incorrect. So you can see, yeah, I will change this. This should be correct. Okay. Next question is which of the following is correct with regards to the cyber physical system? Option A is actuator and sensors are part of cyber layer, which is okay. Second is communication latency is a major advantage of CPS. And third is MITM, man in the middle, falls into the category of false data injection attack. And last is running the most up-to-date firewalls, firmware, VPNs, software is one of the ways to ensure cybersecurity. We have two layers, one is cyber layer and physical layer. In physical layer, we have all these physical components like actuators and sensors. So it's not a part of cyber layer. In cyber layer, we already discussed, we have communication network infrastructure, including the different protocols, communication protocols. And then we have computation or analysis part. And the last part is the control. Okay, that is the cyber part. Communication latency is not an advantage, it is disadvantage. We don't want delays in the communication. We want to be as fast as possible. This is not an advantage, this is a disadvantage. And there are man in the middle is a part, it's a type of denial of service attack, not false data injection attack. But this is not correct, this is not correct, this is not correct. This is correct. Running up to date firmware VPN is one of the ways to ensure cybersecurity. Next question is which of the following is are limitations of demand response for frequency support services? Limitation of demand response for frequency support services. So can demand response be used to provide all kind of frequency support services? If not, we have to see. So first is unpredictable demand response. Yes, we don't know because we don't. It depends upon the behavior of the consumers, and we don't know that. It's very unpredictable. We don't know whether they are going to respond to a particular price signal or not. We don't know is whether the incentive which we are providing is sufficient for them to behave in a particular way. So it's quite unpredictable. Second is complexity involved in communication and control mechanisms. Yes, for distribution system, we require a huge network of communication because of the number of consumers involved in that. On transmission system, number of generators are in thousands, but in distribution system, the consumers are in lakhs. The numbers are quite large here, and that's why it makes the communication, any kind of system involved in distribution system, it's quite complex. Third is the total amount of provided flexibility doesn't entirely compensate for substituted conventional synchronous generator. And fourth, four major ancillary support services cannot be provided simultaneously by demand response. Yeah, that is correct. All the ancillary support services cannot be simultaneously provided by the demand response. That is not possible. So all these are limitations of demand response because it is unpredictable, there is complexity involved, and the total amount of flexibility doesn't entirely compensate for for the one that is provided by the conventional synchronous generator, and it also cannot provide all the kind of ancillary support services. We have all of the above are limitations for the demand response. Now let's look at those. Select the correct outcome with respect to frequency support. Tertiary frequency response is based upon the volume action. Interconnection frequency response in load sharing. Energy storage cannot be used to support service. Response time for frequency services is within primary frequency services is within 2 cycles. We will see this in detail. The tertiary frequency response is not based upon governor action. It's the primary which frequency response which is based upon governor response. Governor action. Interconnection frequency can be energy storage will provide frequency support services. This is not correct. This is not. And response time for primary is also it is in seconds. For inertial response, it is within cycles. Here you can see the frequency support services, the essential reliability services. So the frequency support ensures that the frequency is within the accepted frequency control. First one is the inertial support, where the stored rotating, which is based upon the stored rotating energy. And it is the accumulation of the inherent response of conventional generator that arrests frequency decline. The initial support is the stored rotating energy, and the accumulation of the accumulation of inherent response of the conventional generator that arrests the frequency decline. And it will be provided through the deliberate control of renewables as well. Here, the order of time is cycles. It's for the initial support. And you can see the energy storage system can provide all these services because it is quite fast. It can respond within millisecond itself. And it can also, because the discharge duration of battery, you can see at present we have battery up to 4 hours, but in Australia there have been tender for batteries operating for 8 hour discharge duration. So it is quite large as compared to this 1 hour for tertiary frequency services. So they can provide all these 4 times of frequency response, frequency support services. starting with the initial support, which in the conventional generator is available due to the rotating part, and which can also be mimicked by the renewable energy resource converters by using the concept of virtual inertia or virtual synchronous generator. So that's why it is written that it may be provided through the deliberate control of renewable energy resources as well. This next level is the primary frequency response, and it is automatic. This is also automatic. This is automatic and autonomous. It is based upon the droop and the governor response of the individual generator. And then it can also be provided in the control of the distributed energy resources. And it may include the automatic load shedding as well. And its order, the operation time of operation is within 2 to 5 seconds. The main thing is it is automatic and it's based upon the governor group, and the governor response, and it's possible in the ER as well. And it is in seconds. This was in cycles. That means milliseconds. Here it is in the order of seconds. And secondary frequency regulation services. It returns the frequency. What it does that it returns the frequency to the nominal value, and also minimizes the area power mismatch. So here the area control error plays the role, and it is achieved by the automatic generation control, the AGC. Centralized. This is centralized and it requires communication infrastructure. So this is to minimize the area power mismatch, and this is centralized within the control center through the automatic generation control, the AGC control. The main part here is that minimize the area power mismatch, and it is centralized and operates through AGC, and it requires significant amount of communication. And here some DERs can provide this kind of service also, and energy storage can provide this. And this time duration is between 30 seconds to 30 minutes, up to 30 minutes, not more than that. And tertiary frequency reserve services, response services, these are taken care by the spinning and non-reserve spinning reserves. This is not automatic. These three are automatic. And this is what we consider as a natural response. And these are automatic. And this is not automatic. It takes between 15 to 60 minutes. And they are whenever this frequency service is required, the state, the required, the spinning and non-reserve spinning reserve or generators, they are called upon by the operator to provide this kind of service. So here the correct option was the interconnection frequency deviation can result in load shedding. Others are all incorrect here. Now next question is, which of the following is not an aim of demand response analysis? First one is minimization of total consumption. Yes, we want to minimize that because the problem here is this. See, we saw the curve to be there was a lean day, morning peak, and like this. Okay, so there are two peaks and two leans. There can be only single peak also. This is also possible. In both the cases, you can see there is a lot of difference between the minimum and maximum, and that will result in a difference between the maximum as well as the average and the peak demand. And so this difference between the average and the peak governs the installed capacity. right? This governs the install capacity, and we always want to have this peak equals to approximately equals to the average. We want average demand to be equal to the peak demand. That means the load curve we want it to be flat, because if we see here, then we can say if the average demand is like this, only for these few hours we require this capacity, other which would otherwise be unutilized. So its utilization factor or the plant load factor is quite low, and which is not economical. That's why we want to minimize the total consumption to reduce that peak demand. And reduction of total required power generation, no, this is not the uh, then promote the conventional source, this is not the aim. Elimination of line loading, yes. Line overloading, yes. Yes, so this was not correct. Here you want to find that which of the following is not a name. So this is not a name, right? We want to promote the renewable resource. Yes, we want to reduce the total required power generation so that we can save cost on building peak generators, peak demand generators, and we also want to minimize the total consumption so that the generation requirement also reduces. And we want to eliminate the line overloading to increase the life of the line as well as to improve its utilization to, yes, to increase its life basically. Demand response analysis here. The aim is minimization of total electricity consumption, reduction of total required generation, green and clean energy. That's why we don't want to promote conventional resources. And then finally, elimination of the line loading. These are the aims of the demand response analysis. And the optimization objective is to minimize the electricity cost, maximization of social welfare, maximization of aggregators power consumption, minimization of both electricity cost and aggregators power consumption, both the maximization of social welfare and maximization of aggregated power consumption. Okay, next is which of the following is a desired goal of an utility? Peaky load curve, flat load curve, high peak deficit, less off peak load. We already discussed that. Discuss it that what's the desired goal of an utility? Utility always wants the load curve to be as flat as possible so that the requirement for the peak generation is not there. To save the cost, which is always required. So the option here, the correct option here would be flat load curve. Which of the following is not correct with respect to demand side management? Load shifting demand side management strategy is more reliable compared to other. Okay. Multi-objective strategy provide more peak load reduction compared to single objective. Okay. And demand side management using DC market with PLC is an effective solution to feed the load during peak hours in the present distribution system. Yes, that is true. If we use a BESS, then it will store the excess solar generation during the daytime, which can be used to feed the load during the peak hours in the evening. That is very effective, and we already seen that there are two types of objective demand side management. One is the single objective strategy, and one is the multi-objective strategy. In the single, we want to see it or minimize the deviation between the actual and desired load curve. desired load curve from two perspectives. One is utility and one is the consumer. If we focus only on the one aspect, either utility or consumer, then it's single objective. On the other hand, if we want to minimize, give equal weight, and now it can be equal or different weight also, but the most generic is to provide equal weight, then we would want to minimize this the difference between the actual and desired, right? Actual minus, we want to multiply this by 0.5 into desired load curve of the utility and desired load curve of the uh, consumer. And multi-objective would provide more peak load reduction. Load shifting strategy is more reliable as compared to other strategy. The demand strategy we have in DSM, we have seen three types of strategies. We'd like to revisit that point because it's important. Yes, here you can see. So here we want to minimize the load, actual minus desired. Okay. So these are the 6 strategies of deficit management. One is the peak clipping. We want to clip the peak by reducing the demand during the daytime, not daytime, during the peak hours. By doing different types of things, we can use energy efficient things. The next is the valley filling to increase the load during the off peak hours. Third is the load shifting, where we want to shift the existing load from peak hours to the off peak hours. That means we can defer certain, uh, this will certainly change the consumption pattern, defer the demand from a particular hour to the other, hour. That is load shifting. And then we have strategic load growth, load increasing particularly fashion in a particular fashion, because the entire area might be growing in the same way. So similar load profile is there. So that can be done. The growth is, the demand can be increased in such a way that yes, it is similar to what is there in the existing way. A lot of planning is required in this case. Similarly, strategic conservation, this is possible by using energy efficient devices. And this is the most realistic one. Not realistic, we would say. The most advanced theoretical is this flexible load shape, whatever shape what we can derive that. But it's easy said than easy. It's easier said than done. Easy to say, but it's very difficult to achieve this. We already seen this. Time of use, we have different prices during peak and off-peak hours. Critical peak pricing, even in peak hours, there are few critical hours where the price is even much higher than the price during the other peak hours. Real-time pricing reflecting the actual market um, sentiment directly to the consumer, which is not right now happening in India. We would say that although the distribution companies they are actually seeing the real-time market price, the market price, but consumers they are asked to pay the same amount of, and charges are, uh, I would say the variable or the tariff is same. irrespective of the market price. But what they would do to recover this, they would add different types of component in the bill. In addition to the tariff, they would ask you to provide different types of surcharge, say fuel surcharge, and different types of elements can be added into the bill to recover that amount which was uh, was there due to the volatile nature of the market, electricity market. If the distribution company has had to procure a lot of market mm, s- mm, big much higher amount of electricity from the market, then that too during the peak hours, then the price would their profit would reduce, and to recover that, or their cost would increase. To recover that cost, they would transfer it to the users in the form of different types of surcharge or components in the bill itself. Here, the interact the utility and the consumer, they can have contract where the utility can have a direct control over the different loads which the users have. But for this, we require bi-directional communication infrastructure as well as that control mechanism. That is for that this communication infrastructure is very important. And second one is the interruptible service, where this is also a kind of a contract where the user can be asked to interrupt its service for certain hours. Like it might be like you might be paying some providing some additional then bidding. The demand itself, the consumers themselves can bid in the market. Okay, one is centralized and decentralized. Also, here centralized, each and every consumer work, will coordinate with the aggregator. Each of them will talk to the aggregator individually. This is centralized. In decentralized, they will be interacting with the aggregator as well as they will be interacting with each other. Here, peer-to-peer interaction is there, and aggregator interaction is also there. That's why it becomes very complicated. And here, even if there is some missing data due to communication failure, still we can control can be objective can be achieved here. Okay, so where we okay, so let us check where were we? Yes, we had done this up to here. Which of the following are the communication requirements for the demand response? This is the next question. So option one is quality of service, interoperability, scalability and flexibility, security, all of the above. Yes, we need quality of service, we need interoperability so that we can use uh, equipment from different operators as well as possible. And then it should be scalable as well. And it should be very flexible to accommodate different aspects, different requirement of the different stakeholders involved. We always want it to be secure and fight against any kind of cyber attack. So all of the above. Now next question is the energy related demand response. We have two: task related demand response and energy related demand response. In energy related demand response, time is not important. We can time is fixed, but energy can be changed here. So only the it alters the consumption. The operation time of the flexible load, it alters the consumption during the peak load, and it alters both the operation time and the consumption. None of the above. Which one is correct? Because it alters the consumption during peak load. Which of the following is not dynamic pricing based demand response? We have already seen this. Time of use is there because of difference between uh, price during peak hours and off-peak hours. Then this one will be the time of use tariff, and then this one would be the critical peak pricing, and this one will the real time pricing. So TOU is there, critical peak pricing is there, reactive time pricing is not there. So D is correct. Now questions are over. Do you have any doubts? If not, then we can discuss certain things that I would like to discuss. So let us discuss certain things which are very important. We would say we have discussed this point, and let's see here. Let's discuss this point again. In cyber physical system, it will be secure. Security as well as resiliency, these are two important things. Security is to protect against and avoid the increasing threat from cybersecurity. It is based upon protection. However, resilience is on mitigation aspect. To mitigate any kind of harm and to bring the system back to its normal state as quickly as possible. So mitigation and then bringing the system back to its, you would say, restoration, bringing the system back to its normal operation. That is the part of resiliency, and it has physical resilience, cyber resilience. In cyber resilience, there is also communication resilience. The cyber resilience is, you can see here, is to mitigate damages and carry on once systems or data have been compromised. Even if the data system is compromised, still carry on with the system and also isolate the compromised part, uh, make it healthy, and then again connect it back to the system. Then communication resilience, you can include it in the cyber resilience itself. That is very important. So here you can see, let us take example of this. So what we can see here is, let us say this is physical process, here is a generator. Let's say here it is the generator, some generator platform NTPC, NTPC. Okay, let's see NTPC, cargo. Okay, this is a physical process. Now there are certain different types of sensors available in the generator, which sense different types of quantity, physical quantities, which are required to, uh, to monitor the functioning of that particular physical element or the generator here in this case. And once we have those, the output from the sensor, what we can do is we can use it to do certain kind of analysis to see whether it's working properly or not. So it will be transferred via communication channel to the control center, where the computation on that particular output of the sensor would be done, and would and that computation and analysis would be done by that particular element on the output received from the sensor, and then the output, depending upon the requirement, it can take some control actions as well. If the behavior of the system is going away from the desired or the normal behavior, then it can be used. The, the communication network can be used to pass on that information, the particular control action required via the actuators, means via the communication channel to take certain control action using the actuators. Here you can see AGC would work in that case. So AGC would calculate the difference in the tie line flow and then would provide a control action to change the output of the generation so that the particular tie line flow is as per the desired or the scheduled flow on that particular tie line. So here physical system are all analog system. It can be a plant, it can be a process, it can be actuated as well. They would say this is the physical part and this is the cyber part. In physical part, we have processes, plant, actuators, etc. In cyber part, we have communication, we have computation, and we have control. The IEDs, IoTs are the communication, computation, and control aspect. Sorry. Let me have a sip of water. The cyber is having communication plus computation and plus control system. So all these three are part of cyber system. Because the physical is actual physical process and it's purely analog, and control and computation happens in digital domain. So we need to convert this analog into digital signal. And then again we need to convert this into analog so that we can take some control actions via the actuators which actually work on the physical system or physical signals which are analog in nature. I hope this PMU placement was very clear. And one thing which I forgot to discuss is this. So N bus, here let's say what we have is, this is one bus, two bus, three bus. And bus 1 is connected to these three buses. I is connected to these three buses. And you want this bus to be observable. And there is associated PMU in each of the buses. See, if we have PMU at any one of these buses, then this bus can be observed, right? This can be observed. We can know if we have PMU here, we know the voltage here. And we know the current also. So we can know the voltage here. Similarly, here also. If you know any one of the PMUs, uh, if any of these buses have a PMU, then it will be observable. If you want to have redundancy, let's say this line goes away, still you want this to be observable, then we need to have at least we need to have two PMUs. If we had placed a PMU here only, this line is out. Then because PMUs are not available on this bus 2 and bus 3, then what would happen? This would be unobservable. But if we want to take care of contingency also, what we can do, this is X1, this is X2. We can have two PMUs. So this will become a redundant. This will increase n minus, which will take care of n minus 1 redundancy. So this will become x, and summation of xi is greater than equals to 2. In this case, okay. So this was the point which I had missed. So I got, and also one more thing, why is this binary variable? Why xi is a binary variable? How is xi a binary variable here? You can see xi is either 1 or it is either 0. But is and this xi can take only two values. Either it is there in the bus or it is not there. It can take only one and two, one and zero values. And that's why it's a binary variable. Then we make it integer also. One part present, two for absent. That's the formula is used. Here in this case, this is known, this is a linear Application function. But here you can see we have product xi into gi, not this one. So these are also linear functions. This is obtained from these values are obtained by doing the state estimation using the base OPM. Which is the OPM. We get that. Except here, this also we have discussed here. We have also discussed the advantages and disadvantages of cyber physical system also. And we have also discussed different types of attacks, cyber attacks. One is the false data injection attack and denial of services attack. Here we have man in the middle. or suspend the communication. And you can go through these different uh, references that are provided here, and these references are also available. It's available here in the link itself. With each slide, you can find the particular reference, and that will be very beneficial for all of you. And if you have any kind of doubt, you can always ask me. We have discussed these disadvantages of cyber physical system, that it will result in it will result in risk of cyber attacks, and there will be communication latencies. There can be packet dropouts. So this will be dropouts, not be. This should be over here. There can be congestion in the network, and there can be malicious control effects. This also we have discussed. We have discussed. We have discussed. Uh-huh.
एक दशक के साथ केक करता है
Okay, so virtual inertia, let us discuss it once more. So what is virtual inertia? It is to control the IBDGs, inverter-based distributed generators, in order to mimic the conventional synchronous generator dynamics and provide the inertia virtually. What is the source of inertia here? It is the short-term energy stored in the DC link of the renewable energy resource power converters. And what is the virtual synchronous generator? It enables, if we enable the converters and IBDGs to mimic the behavior of conversion generator, it is like virtual synchronous generator. And it provides grid support services. The control application, it's a control application for enabling converters and IBDGs to mimic the behavior of conventional synchronous generators. And it will provide grid support services like inertia, frequency regulation, voltage support, and the very one major advantage here is that we can simply tune it using software adjustments. But very easily we can tune it. So that is a very important advantage here. And we can incorporate that this in the control of the IB, these distributed generators itself. And they will be able to mimic the entire behavior. So that is very essential and very important here, and can be used whenever required. And these are very much required here. Right now, the inertia is decreasing, and as the penetration of renewable energy increases more and more, this inertia requirement will be huge. And you can see, let us discuss this point, that since we have come here, then virtual inertia would say there are certain energy storage. You can see energy storage, which can provide inherent inertia. Can you give some example? So these will be the energy storage which will be uh, having rotating part. Some rotating mass has to be there, which can provide without incorporating anything in the converters. We can have that inherent inertia from this energy storage. For example, one is the pumped hydro. This pumped hydro storage, because it is similar to a hydro plant, but it has a facility that it has a reversible pump that because it operates in it has two reservoirs. So it, when the water falls from the upper reservoir, well, let me just write it down. Okay, where is this? Okay, so this is the upper reservoir and this is the lower reservoir. When water falls from the upper reservoir to the lower reservoir, upper reservoir to the lower reservoir, then there is a generation. There is generation. Right? When water is again sent back from lower to upper reservoir, then the water is being pumped. The same machine is used in reversible mode. Now it's a conventional machine. It can provide the conventional. It's a rotating mass, right? That's why it can provide that inertia. Similarly, can you tell some other energy resources, energy storage devices, or energy storage technologies which can provide this inherent this inertia? Yes, we can. We do have set. For example, we have compressed air natural gas, compressed air energy storage. It has inertia. It has a rotating part. Similarly, we have CO2 battery also. We have many such energy storage technologies which can provide this inertia. Pumped storage is a very good example because and it's a very old technology. We have been using it since many years. And recently in Japan, I think in 2016, one pumped hydro storage plant was decommissioned, and it was based upon seawater. So it used the seawater. It's to operate on seawater instead of fresh water. So that was the first plant in hydro, not so pumped hydro plant, which operate which was operating on this seawater. Rest all the other plants are actually operating on not seawater but fresh water, using fresh water. Compressed air energy storage is there. Then pumped hydro is already done. Then we have this what we call it as uh, okay to say yeah battery and this PV are the main uh, two major elements which do not provide this inertia. So the converter needs to adapt the way to change their converters. And we already discussed that PV is not able to provide the inertia. The battery converter can be designed in such a way that it provides inertia, that virtual inertia, which will be very important in the upcoming years when the penetration goes to a very high level, the RE penetration. This also we have already discussed. So these are the different, this is the operational time scale for different types of services provided by the different generators or different types of operational aspect of power system. Hence it starts with inertial primary, secondary, tertiary response and slow tertiary and then generation rescheduling. It happens every 15 minutes. Not 15 minutes, it depends on the real-time market. What is the real-time market? Okay. And then unit commitment and day ahead scheduling. The day ahead scheduling happens 24 hours before, and then unit commitment is even before. For thermal, it is 3 days before. It's 3 days ahead. So as we move from the left to right, the operational time, the time of operation, that window increases. So we need to take decisions much ahead of the time as we move to the right side. That's why the planning is at different level. It's year ahead, it's decade ahead, year ahead. So it's decade ahead, it's several years ahead, year ahead, it's month ahead, weeks ahead, week ahead, or days ahead, and then day ahead, and then hour ahead. It can be but different time scales of planning is being done, and the operation of system also happens at different time scale. Therefore, we need to take decisions at these different time scales. So that's why we are talking about all these things, different times, different phenomena occurs at different times. That's why we have this 4 stages of time frequency regulation. And for each time we have different types of services which are required, and different types of agent will be there or which will be doing that services. So thank you very much for joining, and we will be meeting next week, same time, 6 to 8, and we will discuss the remaining 4 weeks. Now, next, starting from the next week, the demonstration uh, will start. Whatever we have studied, the how to use that concept to actually validate those things on different loops, on different softwares, hardware platforms, how to actually demonstrate that in the real world on small scale platforms which can be replicated to a large scale. So that we are going to see in the remaining 4 weeks. This was the week 8 and 9, 10, 9th up to 12th. These remaining 4 weeks are all demonstration projects, um, demonstration case studies. So that we will discuss. So thank you very much for joining. We will conclude this session here itself.